Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, what we're going to be doing is test driving the formulas that we obtained for the confidence interval of the expected value of our response variable, and the other one that we obtained for a prediction interval for a particular observation at a particular also combination of values for the predictor variables. Okay, let's begin. So the example that we're going to discuss in this video is this. It's an example that you have seen before, and in this example, remember that the response variable that we were interested in was the plant's electricity usage. Okay, and we had two predictors, in this case CDC, which stands for cooling degree days, and the other one was the plant's production, right? Okay, so we had this data set, okay, and multiple linear regression model that looks like this. Now, instead of having just one single predictor, we have two, and in addition we have y-intercept, if you will. The assumptions for the error, same as always, normal with mean 0, variance sigma square, and the epsilon i's are independent. So what we would like to do is finding a 95% confidence interval for the average electricity usage in a month with these particular values, this particular combination of the values for the predictor variables x1 and x2. x1 5.5, x2 150. Now part B is similar in the sense that we want to say something at the same combination of values for the predictor variables, but the important difference is that instead of a confidence interval, we want a prediction interval. So we're not interested about the expected value at that particular combination. No, we want to make a prediction. Okay? Okay. So let's use R. First step, as usual, let's enter the data. So let me launch R, and I'm going to copy paste this. Okay, Y, X1, X2. Okay, looks good. It seems to be what we want. Okay, if we compare that to our table, yeah, looks good. Okay, so first let's try and find that confidence interval. Okay, let's test drive. Let's see if our formula works. First, let me find the number of observations that we have. So in this case we have 12. Good. Now what I'm going to be doing is trying to implement that formula using matrix algebra. Okay, so as you can see, we need the design matrix X here in our formula. Okay, so let's try and construct that design matrix X. So in this case, remember that we have a y-intercept, so we're going to have a column of ones. Okay, so let me create that column of ones. I'm going to be using the built-in function rep, as in repetitions. I'm going to be repeating 1 n times. Okay, so let's see what it looks like. There we have 12 ones. Now we have the values for our predictor variables for the 12 observations that we have available. Okay, so now X, the design matrix, is going to be, I'm going to be pasting the columns 1, the one we just created, x1 and x2. So 1, x1 and x2. That's going to be our design matrix X. So yeah, it looks like what we want. Now, since we're going to be doing matrix multiplications, I just want to make sure that R knows that X is a matrix. So I'm going to create a matrix with the values of X. Number of rows, well, n. Number of columns, well, it's going to be 3. We have one y-intercept, right, and 2 predictors, x1 and x2. Okay, now same thing for y. We already have these values here, right, but I want to make sure that R knows that y is a matrix. So in this case, number of rows, again, n, yeah, that's the number of observations, but the number of columns is just 1. So yeah, looks nice. Okay. Next, we need beta hat, right? That is going to help us find our point estimate for that confidence interval. Remember that beta hat is given by x transpose x inverse times x transpose y. Okay, so let's try, and now that we have the design matrix X and we have the vector of observations y of a response variable, then let's find beta hat. So we know that if we want the transpose of a matrix, we use that command T and then brackets and then the matrix that we want the transpose of. Let's multiply that by X. Okay, and with solve, what we get is the inverse. Okay, so we could do this times the product x transpose y, but let me do it like this. It's going to be the same, you can try that. So instead of finding the inverse of x transpose x and then multiplying that by x transpose y, I'm going to be doing this. Solve transpose of x, x transpose x and then x transpose y. Okay. Okay. Now, let's see. Okay, looks good. How about we just round this guy to 4 decimal places? Okay. Next, let's find that point estimate. We know that that point estimate is going to be x0 transpose beta hat. Okay. And we know that we have a particular combination of values x1 and x2 in mind. So 5.5 for x1, 150 for x2. So let's create that x0. So x0 is going to be a matrix. We want to make sure that R knows that. 1, because we need to take into account beta 0. Then 5.5 for x1 and 150 for x2. Then we have number of rows is going to be a row vector, right? And we want n columns. Or, yeah, 3 columns. So another way would be just saying that this guy is creating x0 as a column vector and then finding its transpose. Okay? So it's just a matter of being careful on how you define that. Okay? That's why we have to keep track of the dimensions. Okay? Okay, so if you take a look at x0, it's a row vector, right? Dimensions 1 by 3. Then I'm going to be multiplying this guy by, x transpose x. So what I mean by this is this guy that we created here is x0. Or if you want, just to avoid confusion, we could, instead of doing this, we could create this guy here. So it's a column vector, and then we apply the transpose here. We can do that, so we match what we have in our formula. Okay, let's do it like that. Okay, so next, right, what we want is our point estimate. Let me call it y hat 0, this guy here. So y hat 0. So what we want is the transpose of x0 here times beta hat, our guy here. Let's take a look at it. Okay, no problem. Next, we would like to find this guy here, which is a component of the standard error, right? Well, yeah, it's a component of the standard error. We have to multiply that by an estimator of variance sigma square. So let's do that. Let's find that component. It's going to be just x0 transpose times, now let me multiply by solve of x transpose x, right, times x0, right? If we did this correctly, should end up with a number that makes sense. So that means that we have the dimensions, right? Okay, so now we want that standard error, right? So let me remind you that one way of getting the sum of squares for error SSE would be using the matrix H, right? So just saying that we are going to be finding the standard error next. H, remember, is defined like this: X times X transpose X inverse, right? Times, well, meaning you know, matrix multiplication, X transpose. Okay, so let's see the dimensions of H. We should have, since we have 12 observations in this case, H should be 12 by 12. Okay, so we're good. Now, remember that y hat, and let me use a capital Y here because it's going to be a vector that contains the 12 predictions for the 12 observations, and we know that one way of getting those is just doing this matrix multiplication, H times the vector of observations Y, right? And that's where the H matrix gets its name from, because you know, once you pre-multiply Y by H, you end up with Y hat. Okay, so let's see, we should have 12 numbers, right? And each of these are the corresponding predictions for Y1, Y2, and so on, right? Okay, so the sum of squares for the error we can find like this: the transpose of Y times the identity I minus H, right? You guys agree? And let me just remind you why. We know that the residuals are going to be Y minus Y hat, right? But when you substitute this expression for Y hat, you end up with Y minus H times Y. Then you can factor out that Y and you end up with the identity minus H times Y. And then you do that product, the transpose of that vector, which would be Y transpose I minus H transpose, right? And then times I minus H times Y. You know that I minus H is idempotent, is symmetric, and that's why you end up with this expression here. Make sense? Okay. So, oh, sorry, I forgot something here. Now we should be fine. That's better. Okay. So next, let's find the mean square error, meaning the estimator of our variance, sigma squared. Remember that in this case, K represents the number of predictor variables, and K is 2. In our lecture notes, we also used R instead of K, as in the number of regressors. Okay. Well, mean square error is going to be SSE divided by N minus K minus 1. Right? We know that in the case of simple linear regression, it was SSE divided by N minus 2. And in that case, K was only 1. So that's why we had the N minus 2 in the denominator. Okay, so mean square error, good. Let's find the standard error for our confidence interval. So what we want is this. square root of x0 transpose x inverse x0 times s squared, where that guy s squared is an estimator of sigma squared, the mean square error. Okay, so standard error, let's write that down, square root of, let me multiply by s squared, or mean square error first, times, and what we want is, remember that expression that we had here, that we computed here? Yeah, this one here. That's the one that we want. Okay, yeah, okay. Let's see, standard error. Okay, looks good. Finally, we're almost there. Let's find t star. I'm going to be using t star for the critical value, meaning the value from the t distribution that is going to give us, in this case, a 95% confidence. So alpha is going to be 0.05 because we want 95% confidence. We know that if we want to find a critical value using R, we use the function qt as in quantile of t. In this case, right, since we want a 95% confidence interval, we want a number that has 1 minus alpha divided by 2 to its left. Okay, so let's find that guy. Degrees of freedom, we know n minus k minus 1. That's what we want in this case. So t star. Okay. Now the confidence interval, and remember that it's going to be just given by a lower confidence limit, or LCL, and upper confidence limit, or UCL. Okay, so the lower confidence limit is going to be just our point estimate minus that margin of error, and the margin of error is just that critical value times that standard error. So it's going to be just y hat 0, that's what we called it, minus t star times the we called this guy standard error. Okay, so LCL and UCL, right, the upper confidence limit, it's the same but with a plus sign here. So UCL, there we are. So our 95% confidence limit goes from 2.98 roughly to 3.20 roughly. Okay, now that's part A. We have our confidence interval. How about a prediction interval? Let's compare. See the point estimate, x0 transpose times beta hat. So the point estimate is the same for confidence and for prediction intervals. However, here the standard error, that's the one that changes. This is the same, right? But we have an additional 1 times s squared. The critical value is not going to change if we don't change the confidence that we are interested in. If we don't change the confidence level, then those critical values are going to be the same for confidence and prediction intervals. And in this case, we want the same confidence limit level for the prediction interval, right? Okay, so the only thing that we have to change is the standard error, right? We have an additional s squared inside the standard error of the prediction interval. Let's do that. Let me just modify that. It must be here. Let me find it. Standard error, right? So we know that what we want is an additional s squared, or in other words, an additional MSE. Okay, that's this guy here, because we have 1 times s squared. We know that s squared is just another way of referring to the mean square error, and this is the same thing that we had before for the confidence limit, for the confidence interval instead of the prediction interval. Now let me change the name of this standard error. Let's say that it's the standard error for the prediction. Okay, so now let's find a prediction interval, and I'm going to be using the same notation, LPL as in lower prediction limit, and UPL for upper prediction limit. Okay, so now let me recycle what we had before for LCL, but now it's going to be LPL. And now the standard error that I want is the standard error of the prediction, right? So LPL is this, right? Note that is to the left of the left end of the confidence interval. So that means that this guy is wider. The prediction interval is wider, which makes sense because the standard error is bigger. We have an additional sigma hat squared here, right? Now let's change LPL to find the upper prediction limit. We have a plus instead of a minus. UPL, right? So 3.37, and this guy is to the right of 3.20. So yeah, it's wider than the confidence interval. Okay. Now it turns out that there's a nice and fast way of finding these. Let's do it. So we already have x1, x2, and y, right? So using LM, we are going to be fitting the linear model that we're interested in. And now we want to predict. In one case, we want to say something about the expected value at x0, but now x0 represents a combination of values for the predictors, so x0 is no longer a point, it's a vector, right? Okay, and we use the same function that we used before when we talked about this for a simple linear regression, right? We use the function predict, we use the model that we want to use for prediction, the vector that contains the predictor values that we're interested in, and finally the kind of interval that we want. Do we want a confidence interval or do we want a prediction interval? So let's see. Let's do this one first, and then we're going to compare to what we obtained using our matrix algebra approach our formulas. So according to this, the lower limit is 2.9835 and upper limit for a confidence interval 3.200. So let's see. So we set lower confidence limit, okay, upper confidence limit, right? So really close to what R gives you with that built-in function. And now let's find this guy, the prediction interval. And let's find the lower prediction limit and the upper prediction limit. So basically the same, right? So our formulas seem to work, right? And but in practice, I mean, if you have a huge data set, it might be a better idea to use this approach using the built-in formulas from R. I just wanted to show you that yeah, our formulas from our textbook work, the ones that we derived together. Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.